Hello, my name is Lena. I will be presenting a report on the security posture of mobile banking applications in Africa using the OWASP Mobile Application Security Verification Standard. This work is in collaboration with Trevor Chibora, Theonest Bekutangaza, and Asangei. So we all know financial inclusion will enable 7 of the 17 SDGs. But when we talk about the key drivers of financial inclusion in Africa, case in point the Kenya, Senegal, and Ghana, it becomes evident that mobile money stands out as a force in this transformation. Traditionally, the mobile has been used for person-to-person transaction. But the use case for the mobile are quickly evolving in terms of financial inclusion and mobile transfers. One, we see a lot of use cases in merchant payments, bill payments, airtime, international remittances, and now even online trading. So to a user, personally, when I'm using an app, it's a black box. Like this app sits on my phone where my personal data, as well as other applications that do completely different things, sit. And the question we are asking ourselves here, as we provide useful and affordable financial products and services delivered through the mobile, are we taking security and privacy as a consideration to the design of these products? So the study's objectives is to enhance security of financial mobile applications by creating awareness through this report, to understand the vulnerability landscape with fintech apps, and to help organizations achieve their goals in terms of adoption of their financial services by delivering security and privacy as a package in addition to the functionalities. So in terms of choosing the apps, there are a couple of things that were important to us. First of all is, where do we get the apps? We limited our study to Android because of the market share held by Android in Africa. And we looked at 18 applications, and 13 of these were in the e-banking sector. And in terms of the owners of these applications, there are some banks that are operating on banks or financial service providers operating at the national level, regional level, and at community level, or what we call SACCOs. We then categorize these apps on 3 tiers, low, medium, and top tiers. The low, we're looking at downloads. Low would look at 500 to 4,999. Middle will look at 5,000 to 49,999. And then the top is an app that had more than 50,000 downloads, So in terms of choosing a framework, 3 things were very clear to us. One is that we need a predetermined list of checks for any mobile application. Number 2, the evaluation has to be fair. And this is important to us as we are later on ranking the security of these applications. And number 3, the ability to apply defense in depth. That we know that when you're looking at security, risk varies from sector to sector. And financial sector being a more regulated sector, we need to be able to apply defense in depth. And one such framework is the MASVS framework from OWASP. It looks at a couple of things. We looked at resiliency, that's anti-tampering controls. We look at code, how good is the code? And then we look at the platform, that is the Android device it is running on, as well as the operating system that is running on it, and network, storage, etc. This is a snippet of what our raw results look like. And so you will see on the extreme left here, we have all the checks that were done. A couple of checks that were done. So this is like, for example, no sensitive data is exposed via an IPC mechanism. This is in the case of content providers. And then at the top, you will see a list of apps that we have tested. So we'll go through each of the app and indicate whether it fails or passes or it's not applicable in the case of row number 38 here. So if you see not applicable, it means that we did not perform this check due to one constraint or the other, and most of them were because it needed it needed elevated privileges to access, to thoroughly test this control. From the table that you've just seen, we looked at a statistical way of ranking these categories in terms of we should be worried that developers are not paying attention to this control, or this is sort of okay. So in terms of critical, we would say that if there's a control and we're testing this control and 70%, more than 70% of the apps fail, then this is critical. So as medium, we'll look at 55 to 31, and low is below 30. The most ignored controls were around 1. Most apps, 81% of the apps did not enforce automated security and functional app updates. So how an app should behave when there's a new update is that either it should force the user to update if they desire to continue using it, or automatically update in the background. And this is very important because code evolves over time to fix bugs, security vulnerabilities in native code or third-party libraries, or even functional updates. So it will be very strange if an app is using outdated code or it's just stopped working, which again brings usability issues. The second one was the ability to take screenshots of the app. 100% of this failed this test. And this could be either the user was able to take a screenshot of the app, or we could not find, or the platform itself, the operating system, can also take a screenshot in the case where the app is being moved to the background for usability. The third one was about runtime protections against buffer overflows and how to make it difficult for an attacker to exploit a bug. So there are two methods used for this. In the case of buffer overflows, there's canaries, and it's a variable that needs to be set. In the case of making it hard for an attacker, one approach that is commonly used for this is address space layout randomization, and this is done using a variable we call position independent code. So 83% did not set these variables to true. Most ignored controls, we had an issue, we saw a rampant issue on supply chain attacks, and case in point, SSL. So if you're using the SSL library for communication, which is a very crucial part of app communication, then make sure you're getting the libraries from a verified source. And in this case, you will be advised to use Google most of the time. Then there was a case of code obfuscation. 55% of the apps did not implement the basic level of code obfuscation, which is to modify the executable. Obfuscation means modifying the executable such that it does not make sense to unauthorized parties. It's no longer useful to unauthorized parties. So the basic is to change the variable, to shorten the variable names and functions and classes to a very descriptive class name of what the class does, to something like A, for example. There are several levels, but for us, the 55% represents those that did not do the basic of renaming the variables, class names, etc. And then we also saw some issues around use of insecure random number generators and in cryptographic protocols, quite common during VAPTs. Controls in between, we saw these were commonly around the use of emulators or jailbroken devices, and we saw apps between 35% and 25% for this. And then a couple of low, there are things that programmers are getting right, like for example, the local database backups. It says that you could do a backup, but they are encrypted. You cannot pick into it. The use of trusted CAs and anchors, that was well handled. And then exception handling, a control that is actually sometimes Google Play Store, they can contact the programmer if the app keeps crashing a lot. So while we categorize the results by highlighting the ones that were mostly overlooked and the ones that were potentially we shouldn't be concerned about, the results we saw were sort of all over. There's no correlation in terms of this is the application size, this is the download base, or things like that. So this brought us to a question of, we wanted to understand why we are seeing these trends. And to understand that, we decided to ask the programmers themselves to see if we can verify the hypothesis that we had. So we would ask a question like, in your opinion, what can be done to improve the implementation of security measures in applications? And this question will be presented as an open-ended question, and then the same question will be repeated with some options as our hypothesis as to why this is happening. Some of the responses we're seeing are around complexity of security, no clear guidelines of implementing security in the code, and simply supervisors not regarding security as progress when it comes to development. Our key takeaways are twofold. One, shift security checks and put them in the design process of the features. Number two, cut out a dedicated sprint in which product owners and developers actually concentrate on fixing security issues in the functionalities. In terms of limitations of the study, the tests were limited to views accessible without user accounts, and the survey did not perform a granular profiling of programmers' experience and technology stack. Thank you.